Okay, today, network hardware. As we went through the OSI model, we talked a little bit about network hardware. What hardware works at what layer? Did we not? What hardware worked at layer 1? CPU. Now, computers are not part of this. CPU, all that stuff is, when we look at the OSI model, it's somewhere out here, away from the OSI model, not part of it. So layer 1 of the OSI, what were the hardware? Give me a hint, there's 2 of them.
Not the wires, but the connectors.
Not the wires, but the connectors, all that, but what hardware itself?
Well, that's
kind of hardware. The electrical is a definition, but repeaters and hubs.
okay.
Repeaters and hubs were at layer 1. The hub actually really creates a true bus. Everything sees everything at that layer. And then since we had all this traffic out there, we needed to organize it. We went to layer 2. You got your notes here, Josh, right? What are the devices at layer 2? Switches. And we're going to say NICs. NIC, honest to goodness, has got to be a layer 1 and a layer 2 device if you look at it. But if we look at the 4-layer model, the first 2 layers are glommed together into the network internet or the network access layer. So they kind of work together. And then we went to layer 3. What was the device at layer 3? Routers. Did we have any layer 4 devices that we've talked about? Any layer 5 devices? Any layer 6 devices that we've talked about? There are other things as we go on. Any layer 7 devices that we talked about? Not really. Huh?
Well, I mean, we kind of talked about the bolts and everything.
That was way down layer 1. Layer 7, do we talk about layer 7 devices?
What's layer 7?
Huh?
That's the same thing.
Layers? Yeah, layer 1 is the lower layer. That's the physical layer of 1 through 7. 7 is the top layer, the application layer. Did we talk about any layer 7 networking devices? We will. We haven't yet. Firewalls, but where does the firewall run? We didn't really talk about firewalls, did we? You know they exist, but did we really talk about firewalls?
No.
Firewalls really filter at layer 3 and 4, and we'll do that, but that's the topic of another class where you can pound your head again, throw things at me again. How do we keep stuff out? How do we actually protect the network? But that's a separate issue. Right now we're just trying to get that little bit of information encapsulated down the OSI model across the routers. And what did routers do? What did they find?
The network.
They found networks. What actually finds the individual computer? Get good notes. What actually finds the individual computer? The MAC address. And what protocol is ARP. I just keep saying those things. Yes, these things do become important as you go through this. What's important about ARP? The MAC address. Hey, that's the way we create a man-in-the-middle attack, by faking it. We'll do that in the security classes. So networking hardware here a little bit. So how many devices do we really have to talk about networking hardware? Back to layer 1, we had 2 devices, right? And I don't have a repeater to show you. We used to have one that ran on coax, and it hadn't been around for years. The active, the ones you plug into, hubs and switches, are repeaters. They regenerate the signal. And the difference between a repeater and an amplifier is a repeater regenerates an amplifier, amplifies everything, including the noise. So amplifier wouldn't do us a whole lot of good if we got a noisy signal. So the objectives for today: identify the functions of LAN connectivity hardware. You can probably already do that, can't you? I mean, really, you can. We'll go through this thing, and then we'll have some lab time. Install and configure a NIC. You probably aren't going to have to do either one of those. This goes back to, and they still in their test kind of ask questions about when you actually had to go plug one of these things into a motherboard, and there actually were configurations that you had to do either by changing jumpers, which are basically just changing the connection, or through software configuration. Have you seen a motherboard lately that didn't have the NIC built into it?
Not in a long while.
Not in a long while. It's just like we say that, hey, we're going to have to add, and we'll say we're going to have to add these wireless cards to laptops. Oh, yeah? When was the last time you saw one without a wireless card to come on it? So, I mean, yeah, it's been yeah. They're there. Okay, so the NIC itself is generally going to be built onto the motherboard. So install and configure a NIC, not so much. Plug and play, really good. Some of you probably remember when plug and play was plug and pray.
Yeah. I remember
when they first in Windows 95 well, what happened there was an awful lot of hardware out there that claimed it would work, it really wouldn't.
That was the video when they first
Oh.
you see it go blue screen.
Yeah.
Or a printer.
Yeah.
Yeah.
Problems associated with connectivity hardware. What are going to be the problems with it, do you think? If a NIC fails, it's only going to fail on one machine. If a switch or a hub fails, it's going to kill everything. And you just kind of got to think about what can actually cause this number of things to fail. An individual machine could be the port on the device, could be the wire, could be the NIC. Generally, it's going to be somebody unplugged it or something like that. Or somebody unplugged or tripped over the switch or the hub. If everything fails, check the power first. Honest to goodness, check the power first to be sure it's still running. Factors involved in choosing a NIC, hub, switch, or a router. The factors involved, what are your factors involved when you choose? And what you probably going to choose at home is a router switch, right? Home router. What factors do you look at? Price? Me too. Absolutely. Durability, power, range. You're talking wireless and range.
Yeah.
How about the number? How many computers are going to connect to it? You may want to consider the number of ports that are available on it. When we get into these higher level ones, we talked a little bit about how the switch makes a list of, in its MAC table, CAM table, of ports and MAC addresses. You may want to consider how big that table can be. Those kinds of things. How fast is the switch? What kind of switch? Pricing, a big deal. Yes?
Hey, for whatever reason, and I don't know why I'm bringing this up now in the middle of everything, I could not log on to my virtual machine and do my...
Okay, we'll work on that after we get through with this. Yeah. Honest, that happens sometimes, and I don't know the answer. The functions of repeaters, hubs. Here's a new one that we hadn't talked about. We haven't talked about a bridge yet, have we? It's a layer 2 device. What a bridge really is the predecessor to a switch. A switch is sometimes called a multi-port bridge. So what a bridge does is separates at layer 2 network segments so that we can do that thing. Switches, routers, gateways. Gateways is something that can be at any layer. Gateway is another one of those terms that, what is it? A gateway, on a computer you put in a default gateway, which is the address of the router that tells it that if you can't find it here, go let that guy figure it out. That's a different that's topic of a different class when we do routing. A gateway also can be a piece of software that allows a PC to connect to a mainframe. So gateway and gateways can appear at, that kind of gateway can be at any layer of the OSI model. So we do have some 4, 5, 6, and 7 devices now. It's called a gateway. And the OSI model layers at which they operate. And again, I tried to do some of that as we went through this thing. The types of routing protocols. They kind of jump around. Routing protocols will do that. What you basically need to know at this point in time is the letters, and kind of have an idea that, yep, that's a routing protocol. We're going to have dynamic and statics. Statics, we have to put in the addressing. Dynamics, they figure it out on their own after we do the configurations. NIC connectivity device that enables workstations and servers, and this is a really old one. This is on an expansion slot that you'll probably never see again. It's an ISA industry standard architecture, which is way back when. It's a 16-bit arrangement. But what these things do usually contain a data transceiver, transmitter, receiver, so that you can send the signal, put the signal on the wire, and receive the signal. You made wire, you'll use 4 wires, right? 2 pair. 2 pair were for transmitting and 2 pair were for receiving. The reason you had to do the crossover for like-to-like devices is so that when you transmitted and you cross that thing over, you cross the pair, the transmit signal went to the receive wire, to the receive portion of the other device itself. The unlikes, the reason we do that, that takes place inside the switch or the hub if we have unlike devices themselves. Apply the data signals to the wire. We talked about that early on, and the definitions, and these are all, that's why I say it's a layer 1 and a layer 2 device. These are all at layer 1. Assemble and disassemble data frames. Now we jumped up a layer. So it is a layer 1 and a layer 2 device because the connectors, the voltages, all that stuff is layer 1. And that has to happen here because we put the information on the wire. It also has the MAC address, the media access control address, the layer 2 address, the built-in address, burned-in address, physical address. And it assembles and disassembles data frames. So it frames, it puts some organization on the data itself. Interprets the physical addressing information. The MAC address, how do we get the information to the final destination? That's the MAC address. We get to the network, and this room's a network, and I keep saying that in this building, each room, many of the rooms are on their own networks. You get to the room with the router, with the IP address, the layer 3 address, the logical address. You get to the actual device itself with the MAC address, the physical address, the layer 2 address. IP addresses are 32 bits. MAC addresses are 48-bit hexadecimal. Half of it, the first half is the manufacturer, the second half is actually the serial number. Determine which node has the right to transmit data at any given instant, and how did it make that determination? In an Ethernet. What were those letters? To determine if you can transmit information, that's saying, can you get onto the media? Anybody remember the letters? About CSMA-CD. Carrier sense multiple access collision detection, right? That happens, layer 2, that happens with this device. Can we use the media? Is anybody transmitting? And when we say that, we're really talking about a true Ethernet here. Variety of types, access method. What are the access methods that we really talked about? What were the 2 major types of media access when we talk about access, media access? Were the CSMA-CD, the Ethernet, and what was the other one?
Bounded and unbounded.
Bounded and unbounded. How about the one that goes around in a circle? Ring. Token ring, token passing. How do we get access to the media? Network transmission speed, and when this book was written, the transmission speeds were probably like 10 and 100 megabits per second. Now we're talking 1,000 and 10,000 megabits per second. 100 megabits per second is kind of mundane, isn't it? Everything does that. Gigabit is becoming pretty common, honestly. 10 gigabit is getting into the lands pretty quickly. We can send this stuff pretty quick. What happens there if you make a mistake? Boy, you really screw stuff up real fast at 10 gigabits. So things happen faster. But they have to happen faster, don't they? Anybody remember way back when the internet was in its infancy in the early 90s, late 80s, early 90s? 92, 95. How many pictures did you actually get? When you went to a web page, what did you normally get? Text. So we've made them really attractive with all of the images that go in them, videos, all that stuff. So we really need all that speed. Anybody go to a website lately and just look at the text?
Yeah.
How fast is it? It's like instantaneous if you don't get all of the other stuff. One of the other things that I kind of like to do when we do these open houses is to take Ether-Ape, the thing that's running up front, put it on a machine and go open up a couple of websites like ESPN.com and CNN.com and see how many places you actually go to. You're probably opening 15 or 20 websites when you go to one of those pages. Is that going to mean we need the better connectivity? And we do need the better connectivity in order to do all of the stuff that we do. Type of compatible motherboard or device, what that means is you got to have the right bus, you got to have the right plug. Just like electricity, you can't plug a 220 volt plug into a 110 volt outlet. They're physically different, so what can we put onto the motherboard? The NICs themselves, probably not going to be a big deal because I think anything that you buy today is going to have the LAN card built into the motherboard itself. What happens if that dies? What happens if it quits? What you going to do then?
Buy a new computer.
You can buy a new computer. I just go buy a $5 NIC and plug it into an expansion slot. Nah, you don't want to do that.
What if you have your slots all filled?
There are, well, you may have to make a decision. There are some hardware out there that will allow you to expand the slots. And that goes back to what kind are you going to buy? Are all your USB slots filled? You can buy a USB NIC. If the USB slots are all filled, what do? Buy a USB hub. Because that's all that is internally is a hub, the number of connectors that are on that. And you can go up to probably more. I'm trying to think of the number. It's somewhere around 200 and something. I don't remember the number of devices, USB devices, that can go onto a machine. Somebody did that one time with mice. Can you imagine having 200 mice on your computer? It's bad enough when you have two. But the manufacturer, if you're worried about the manufacturer. When we talk about the devices, I brought these motherboards in so that you can see the slots that we have now. The old slots are on these motherboards that are over here on the wall. You can take a look at those. But these new ones, this one has PCIe, which are going to be the fast ones, and I was just looking at those, and they go from like 500 megabits per second to just a little under 4 gigabytes per second, depending on which ones we have. And these both are PCIe. You got a single lane, and they go on lanes, a single lane and a 16 lane. So the 16 lane, it's got 16 of the single lane speeds.
Yeah.
When you pass these things around, try to handle them by the edges. I don't know if they're good or not good. This one on the bottom, I would say maybe is, maybe isn't, but these are moderately new. And if you look on them, it's got the NIC on it. I'll leave this one in the anti-static bag. You can see through it. It's got some different expansion slots on it. It's got just a straight PCI, which can be a 32 or 64-bit, depending on how it's built. And it's got, here is going to video slot called AGP, and it's got the memory and all other stuff on it. But each of these, if we look at the back, has a place to plug in your RJ45. So they've got the NICs built on it. You're going to have to install and configure them, maybe if that dies, but that's about it. when you do those things. I know some of you have looked at these things, built machines, played with motherboards and all that. Some of you haven't, but those are there. That goes back to the type and compatible motherboard device. You've got to buy a device that fits the expansion slot that you have. Do all of them have a lot of slots? Not anymore, because most of the stuff comes on the board. If you look at these old ones over here, they got a large number of slots on them typically. The new ones, that first one's got, what, a couple of PCIEs, and that's about it. This one's got 2 PCIs, I think, and a video card. That's about it. So we're going to do those things. The internal bus standards, circuit used by the motherboard to transmit the data to the computer components. The bus standards are what we put on these things, the PCI, PCIe, ISA, whatever we're going to connect the devices to the CPU with. Memory, processor, hard disk, NIC. Hard disks, we've gone from IDE to SATA. Serial, yeah. SATA, SCSI, IDE, a number of different ways that we connect. And again, the motherboard has to support those things. The one that the one that Tom has there has got right here are the SATA connections for the hard drives. I guess both of these actually have, both of these have SATA. So how do we connect these things? And you've got to buy the equipment, use the equipment that is supported by the motherboard itself.
If I remember correctly, the little guys here.
Those are single lane PCIe.
Yeah.
And that's a 16-lane PCIe. And if you look real close, it says right on the motherboard.
Yeah, I haven't seen the use for them. I remember that they were.
Oh, well, these wireless NICs on these machines that are in this room are all single-lane PCIe. Yeah.
The only weird slot I've seen like that is they were going to do a physics engine for gaming. NVIDIA bought it and built it into the
it depends on whether you do a single-lane or a multi-lane card. I mean, these devices, the ones that you see that got the antenna sitting on top of them, they go to a PCIe, single-lane PCIe, yeah. Yeah, these machines have the wireless on it because we have a wireless course that we do in this room. Capacity, the width of the data panel, and we'll talk a little bit about that when we do the PC repair class. Clock speed, how fast does it actually go? Clock speed is what manufacturers advertise, isn't it? Processor, they don't really advertise clock speed, they advertise processor speed. The processor is some multiple of the clock at any point in time. Expansion slots, beat that one to death, I think, allow you to add devices. You have to buy the devices that fit the expansion slots that you have when we go into those things. The PCI, say again? Yeah, the PCI, the second one has a PCI slot, 64-bit, 32 or 64-bit, and it's going to be a 33 or a 66 megahertz clock speed, which is going to be substantially slower than the PCIe clock speed. PCIe really is the popular one today. Maximum data transfer, 264 bits. ISA is something, the original slot, and that's what this NIC goes into, is an ISA slot. The original expansion slot, hopefully you're never going to see one of those for real. PCI Express, 64 bits, 133 megahertz clock speed. When this was built, there are actually, I think now 4 standards of PCIe, and they basically double the speed with each generation. Generally double the speed with each generation of this thing. 500 megabits per second data path, that would be the PCIe first generation, 2, which is the 2. That'll be 1. 2, I think 2 is a gig. 4 is like 4 gig. It's nearly 4 gig. Those are things that you can look up. Picture of, and the reason pass these things around what we have, they show on ISA. This is something that you will never see, because the standards, the ISA, PCI, and PCI Express, you're not going to see on the same motherboard. You're not going to see ISA anymore. AGP and PCI Express you won't see on the same motherboard because the standards aren't compatible. If you have PCI Express, video is going to be PCI Express and not AGP. If you got PCI, then you can have AGP Advanced Graphics for the graphics card. PCMCIA, you may or may not ever see one of these things. This is going to be a wireless card that goes into plugs into a machine. PC card, the first PCMCIA, and it goes on card bus. What they are a credit card looking affair that plugs into the side of a laptop. Most laptops don't have those anymore. They're built in, but if you wanted to put one on, what would you use?
Oh, you mean they don't have a slot anymore?
No.
Yeah, they do.
Mine doesn't.
Really?
Yeah. The new ones generally don't have that slot anymore.
Last Dell I bought was a
They may,
just above the hard drive.
They may or may not, but the last one that I bought did not have that slot. This one, I thought did have that slot. We've broken the light on this one. This is one we take apart. I thought that was it there. Yeah, that's it right there. Yeah. PCMCIA slot. Can you get that to pop out? Yeah. This is the placeholder that would go in there. You take this out and put the PCI. It's about this size, so it's something like this.
Where's the hard drive?
Still use those.
On this one, I don't remember.
The RAM.
So insert this in 10100 LAN, PCMCIA expansion card for a laptop. What we're going to find there are wireless connectors. USB, and see 1.1, 3, 2, and now we're up to USB 3, right? USB 3 is pretty good. Firewire, IEEE 1394, Firewire was originally designed to work on Macs. It's been ported over to PCs. Yeah, Firewire you're going to find built into some machines and not others, but it is a standard on Macs. It's a little faster. Well, it used to be a little faster than USB. USB 3's kind of overtaken the Firewire. Yeah, I had a camcorder. That's exactly what it did. It had a USB to Firewire adapter that allowed you to transfer the stuff from the camcorder to the computer.
You had a Firewire to USB adapter.
You had to have a driver, huh? Because it was Sony specific. It could only be used to transfer the movies from the Sony camera to the computer, and it didn't work past Windows XP. Oh no, there is no Windows 7 driver for that. So you run into driver issues constantly.
Oh my goodness.
This is old, but this is a USB RJ45. If it died and you had used all your other slots, or if it died in your laptop, anybody ever tried to do an expansion on a laptop? Yeah. Had any luck? No. Laptop is basically what you see is what you get. And if it breaks, they generally go into that stack back there, so that in the computer configuration class, try to get the name right, we can take it apart and you can see what a pain it is to take one apart, put it back together. Painful. Onboard NICs, talked about that. Motherboard uses onboard NICs. Most of the everything's built onto the motherboard now, isn't it? Yeah. We got the NIC is, the wireless card is, video card is. I know you gamers, those are not good enough video cards. That's okay. What else do we need? keyboard slot, of course that was always there, the keyboard BIOS and the keyboard connector. The mouse connector, because we use USB for most of that anymore. The USB hub is built on board.
Pretty decent sound card.
Pretty decent sound card, sounds on board. What else? What else do we use on these things? We use USB printers or wireless printers now. So those are there.
I think I still have a serial port.
Some still do and some still don't. The new laptops, for instance, mostly don't have serial ports.
Yeah, you've got 100 of those.
Which kind of makes it painful when you're trying to configure your routers, because if you're going to connect it to the console port, guess what you need? You need a serial port, because that's what the cable uses. So, and then we got to go out and find an adapter. Now we have a USB to serial, the serial to the RJ45 converter, and this goes on down the line. So as things get better, they get better, but sometimes you've got to go innovate with what goes on with these things. Many new computers, most new computers, I hate to say all because you can always find an exception, are going to have all these things integrated into the motherboard. They can be changed. Wireless NICs, and you see we have some really modern ones here.
I like that one with that antenna right there.
We have some of those.
Okay, that's an antenna to fix something up, though.
Well, those we used in we at one time had a set of machines that was wireless because they were in an area that was a cement floor, but it became too difficult to try to wire the room at that point, so we built a wireless. Wireless are pretty easy to put in, pretty quick to put in. The room 117 or whatever it is where the nurses use came with, and these wireless actually came in those machines. But they came in on a Saturday and said, "Hey, we want this room up and running on Monday." How long would it take you to run 20 wires to that room? So what's the quick way to get it up? Put in wireless. Found some issues there. Learned some lessons that are always in the good lessons. Don't ever put your wireless access point where anybody can touch it. First thing they did was break one of the antennas off. Second thing they did was reset it. So it was now on the wrong network. And they couldn't figure out why they couldn't get out anywhere. So that is an, oh, by the way, yeah, put it in the ceiling. That's exactly right. That's where it should go. And then you only need to run one wire so that the wireless can then go back to the NOC on that network. With the different ones, USB, and there are a number of USB wireless NICs that are available. They work pretty well. If you go up and look at the stuff up there, again in the front, one of the things, there's a little USB connector in there, which is a spectrum analyzer that runs on the wireless spectrum analyzer to look at these things. The PCMCIA or PC card, the PCMCIA and the PC card look very similar. The dimensions are a little bit different, and that's where you get into you got to buy the right thing. This one here, the one with the antenna, we actually do have some of these around, and these are going to be really, really fast, you know, like B standard wireless. But they go into an expansion slot of some sort. That looks like a PCI expansion slot, doesn't it? Yeah. Installing the NICs. We're going to click through this. This is in the book if you want to read through it, if you ever have to do this. Are you going to have to do it? Odds are against it. Because what
Hardware, then software. Can you even do that in reverse?
you can, but you don't have to. What do you do when you install something now? Plug it in and wait for Windows to find it, right?
Absolutely.
Or wait for even Linux to find it. Linux is plug and play also.
Complain about it when
So
it doesn't go right.
plug and play, yeah, well, plug and play is a reality, and it actually does work. The other thing is installing the NIC, you're probably just going to plug it into the one on the motherboard anyway. Not a whole lot in those. Multiple NICs can be installed, and they're still probably going to find themselves correctly. If you had an operating system, and we did this for a long time, we used Linux as a router, as an internal router, because we didn't have a physical device to do that with. put multiple NICs into the Linux machine and just used it as a router. Was it ideal? No, because routers are designed to route. Computers are designed to be kind of like multitasking devices. They're not really optimized for anything. Routers are optimized for packet forwarding when you go through those things. The DIP, and I guess the only thing you really need to know about that is DIP is dual inline package. It's just it's just some switches that are inline. I was trying to see if there's anything in here that actually has a DIP switch on it. I'm sure there is somewhere. Or maybe there isn't somewhere. Or maybe not. It's actually a pretty old. See, here's that NIC. Here's that wireless NIC with the antenna on it. Over here on the board. You use those at work? That speed? 802.11b? Really? That's pretty slow. B's pretty slow, though. If that's all you need, that's absolutely right. If that's all you need, it's all you need. May or may not do those things. Properly inserting PCMCIA. Device drivers. The device drivers are going to be with it. Huh? Yeah. Well, that's going to be that's where the PCMCIA card, standard NIC.
It's like a 4-inch thick laptop, right?
Yeah. Oh yeah. Wow. Yeah. Yeah. This is not one of the new ultra lightweight laptops. Device drivers. What are device drivers and why do we need them?
It's an iPad first generation.
Like it takes up there, allows the software to properly communicate.
Allows the hardware and the software to properly communicate. It's the converter that goes from one to the other, and different drivers, different things. That's one of the upgrade issues with Windows, isn't it? Do the drivers work properly? Typically, it's going to be do the video drivers work properly. XP software, NICs and the drivers usually download. And Windows 7, anybody had any real issues with Windows 7 finding stuff like that? It's a pretty smart piece of software. It'll go find most of the drivers for you, which is pretty impressive, I thought, the first time. First time I did one, it was odd. Sorry?
The only problem I ever have with it is knowing to give up.
Yeah, yeah.
Something in and it hung for about half an hour.
Yeah, waiting, trying to just keep trying, so. Drivers, you usually get the driver with the device. You can download the driver from the manufacturer's website, or if it's a Dell or something like that, from their website. They generally going to have proprietary drivers. And if you try to upgrade a laptop, be careful because that's what's going to be the issue. You're going to get done and something not going to work because it didn't have a driver, or you didn't take the drivers with you with the wipe and load. You do need those things. NIC drivers on a Unix or Linux depends on which one it is, and there's a whole bunch of different Linuxes out there. It's gotten pretty good too about finding everything. For me, with the exception of the printers, they still not so straightforward to me. But each one of them is going to operate a little bit differently. The LED indicators. Activity, link, transmit, and receive, blinking, and you can see those things. Different NICs have a different number of lights on them. The link light just means that it's actually plugged in. And if you look at the ones on these machines, they've got a link light and they've got a transmit receive light. You can probably see these things that's got green lights, and they're all going to be different colors. But there should be a transmit and receive so that we can see that what's actually going on. Activity, if it's blinking a link, if lit, the NIC is functional. I guess. I don't know that that's a good statement. It means that it's functional at somewhere around layer 1. Does that mean that anything else is going to work on it? Yeah, it probably goes up to layer 2. Can we actually connect this thing? And when it is functional, you can see the light up on the switch too. If you can see the switch, you'll get a light on the switch and the link light on it. Transmit and receive blinking says that it's at least trying things. IRQ or interrupt requests, things that we used to have to get really involved in machines, but we don't anymore because plug and play kind of takes care of all of that for us. What it does when you start the machine up is it inventories all the devices that are on the machine and assigns them IRQs. IRQs are like a direct connection to the CPU that says, hey, I need processing time. So it interrupts the processor to get it to do something for the device itself. The IRQ conflicts used to be an issue. They'll be reported. IRQs can still sort of be an issue if you get multiple devices that can only use a limited number of IRQs. Memory ranges of these things. The base I/O port specifies the area of memory that will act as a channel for moving the data between the NIC and the CPU. How are you going to connect to the device? How are you going to connect to the CPU is really what we're talking about here. This is not RAM memory. This is the I/O port in the memory area for the CPU that actually allows the connection to take place. Hexadecimal notation, lots of different ports. We're still 2 to the 16th, so we have an awful lot of ports that are available. When PCI actually started doing what it was, which is actually IRQ sharing, so we connected, used a port. Kind of like a socket, we use an IRQ and a port number to connect these devices. That's why we don't have the limitations that we used to, because we used to have 16 IRQs and about half of them were already spoken for. So you had a very limited number of devices that you could put on these things. Firmware settings, the NIC's transmission characteristics, and you're not going to modify these. The firmware settings would be like the IRQ and the port number that it would use. In the EEPROM, I always thought that electrically erasable programmable read-only memory. Does that make any sense when you say all those words together? If it's read-only, then it can't be written to, right?
You would think so.
But it's not normally written to, but it can be. You can actually change those things. And that simplified things in computers when they went from ROMs or PROMs, programmable read-only memory, where you had to do it with ultraviolet, to electrically erasable, so that you can upgrade the BIOSes themselves. And that's what the BIOSes are. That's what allows their upgrades to take place. Huh? With an you had to take it out, take it out, and use an ultraviolet light. If you look at ROM chips, they have a piece of tape over them. If you take that piece of tape off of them, there's a window there that allowed you to rewrite the ROM, or to destroy the ROM if you took it off in the right light.
Sweet.
Yeah. That's part of the history that I'll look at a little bit in the other. Ultraviolet, yeah.
Just hit it with an ultraviolet.
Well, you had to do it. You had to have a programming device to do that with. And those are actually the new ones. And if you looked at these boards, everything's soldered in. Those were actually, you could pull them out.
Right. I noticed that one has little sockets on it.
This one has little sockets on it to do things. Yeah, some of them do. Some things do, some things don't. The right NIC, and you can look at this thing. Why would we want to do it? Load balancing, dual channels. I'll be honest with you, if you put 2 NICs on a Windows workstation, they can get really confused. Yeah, because if you don't know where to go, especially if one of them's disconnected and don't know where to go, it'll send it to that NIC and then have any place to go. And you're not connecting. And it doesn't always happen. To be on the safe side, if you've got 2 NICs, one of them's not plugged into anything, disable it. Then it can't go there. If you've got multiple NICs in a Windows system, the only thing that you would really want to be a server, because it can act as a router. Workstations, probably not going to do that. Actually, you could do that. You could do that with internet sharing, couldn't you? If you wanted to do that, but most people are using wireless access points or switches at home and not trying to use their computer as a access point to get these things through. But you can share the internet through your computer if you need to, and you would need dual channels. You need multiple connectivity in order to do that. They're going to be on different networks. Power management, power saving measures. One of the things that Windows does for you, by the way, is by default it says, oh, let Windows control this device and save power. Yeah, except when it goes to sleep, it won't wake up, or you're trying to get to it. When you get in an environment like this, the NICs go to sleep. Well, golly, now I want a remote desktop to one of these machines.
You can set it to where the network can wake it back up, supposedly.
Yeah, but you have to send it a magic packet. Yeah, wake on LAN?
Yeah.
Yeah, that works real good. I shouldn't say that. That does work. Sometimes it works better than other times. RAM buffering, upgradable ROM. And the upgradable ROM is the EEPROM. You can download the upgrades to these things. You can do that with your machines too. It's still, and this is just me, but upgrading ROM still scares me to death. Because if you have a problem during the upgrade process, you just ruin the device. Repeaters and hubs. Let's take a break and then we'll do repeaters and hubs and routers. Ready to finish this up? Repeaters and hubs. Active hub is going to be a repeater also, and there are devices that are repeaters. The only thing they do, they don't distribute more than one signal. A hub has multi-port, so what a hub kind of winds up being is a multi-port repeater. It does repeat the signal, can connect more than one machine. The typical one, commercial, you're going to buy is going to have 24 ports on it, just like a switch is going to have 24 ports. I don't know, except for specialized circumstances, why you would want to use a hub. Let's think about it just for a minute, and we'll kind of mix hubs and switches here together. What does a hub really do? It's a physical layer somewhere in here suited only to the bus topology networks. If it's a bus topology, what does that mean for real? That layer one. Probably going to be half duplex. You can think about it as a two-lane highway with a one-lane bridge, really. So it does have collisions. Will have collisions. It's going to be probably slow. Mostly they're going to be 10 megabits per second. They are a true bus, so everything sees everything. We've got no security, no isolation of traffic. And we can't do things like, well, I'll say the word port security. We can't configure it so that we can control which machines can connect to any of the individual ports. So if it's available, you plug it in, you're on the system. So they are, and did we cover all these points here? Physical layer, we knew that already, right? Cannot improve or correct bad or erroneous signal. That means that there's no checksum, any of those other things that we had, so that we could run the same algorithm, see if we got the same results, see if the information was damaged en route. Regenerate the signal over the entire segment. And that's, we really do want to regenerate. We don't want amplification, we want regeneration. One input port and one output port, suited only to the bus topology networks. These things have uplink ports, and if we're going to connect hub to hub, hub to switch, we're going to use a crossover cable. Now, some of them, most of them, if you look at those switches on that shelf in the back, have a switchable port. You can switch the port. If you only have straight through cables, you can switch the port so that it becomes a crossover on the device itself, so that you don't actually really have to make the crossovers. Now, when we go to switches, they don't have any of that. You're going to have to actually make the crossover if we're going to connect a switch to a switch. So, hub, layer 1 device, collisions, true bus. How many collision domains do we have in a hub? One. That's why we have collisions. A hub repeater, more than one output port, multiple data ports, operate the physical layer. Uplink port allows a connection of one hub to the other, and a lot of them do have uplink ports on them. And if you look at those in the back, you'll see some of them are labeled as uplink ports, depending on what goes on there. Ethernet networks serve as a central connection point or a star, so it's going to be a logical bus and a physical star. Again, the star is a physical topology. Hubs are called MAUs, multi-access units, on token rings. Share the same bandwidth and the same collision domain. Connected devices share the same amount of bandwidth in the same collision domain. If you're going to do this, you're going to have a lot of wait time, don't you think? Because only one device can actually be communicating at the same time, at any given time. Now, those times are really short. And when you talk about computers, we don't have any troubles talking about, and I'll do a number that I can do the arithmetic on. We don't have any time we're talking about a gigahertz, do we? What does a gigahertz really mean? It means that it's doing something every billionth of a second. That's pretty fast. When we talk about 10 megabits per second, yeah, we got to share it. That's not real fast by today's standards, but it's still not the slowest in the world. These things, yeah, I said, not the slowest thing in the world. They are slow compared to everything else. Did an experiment one time in a room unintentionally, but somebody got hooked up to a hub and somebody else was hooked up to a switch, and they were both downloading the same file. One of them was like 5 minutes, the other was like an hour and a half. Guess which is which? Hubs can cause issues, collisions, and as you get more traffic on them, the collisions become worse, just like as you get more traffic on a highway, collisions become worse as we go through those things. Type of hubs: passive, intelligent, standalone, stackable. What you're going to see is hub. Stackable, basically, those are all stackable, and if you'll notice that they're vented out the side of them, is what we're really talking about. Passive hub you're not going to see. Passive hub is one that doesn't actually regenerate. It's not a repeater. A bridge is analyze incoming frames. Okay, so what we're going to do with this thing, okay, a bridge, oh, we got this here. Bridge connects network segments. What's a segment?
Just part of a network.
Part of a network. In the PDUs, what was the PDU at the transport layer? It was a frame, right?
Yeah. Transport segments.
Yeah, transport segments. It's a little high from where we're going, though. What we're talking about here are network segments. And this is one of those times where same word, and this is what's really maddening about networking. Same word can mean entirely different things depending on what we do. What we're really looking at here, we'll have a mess. Now let's just go. Try to do it this way. What we have is we're going to have our bridge here. And we'll connect it to a bus. And we'll connect it to another bus. We're talking layer 2 here. So these are the segments at layer 2. So we have multiple computers on each of these buses. So we have these. So what addressing are we going to be using at layer 2?
IP address?
Let's try MAC, yeah. IP, network layer.
That's all right.
And these are going to be hexadecimal. Let's use really big hexadecimal numbers. Huh? Oh, the big ones? Yeah. But I had to get bigger here because I ran out of, hex only goes to F, right?
I thought it goes to,
F. 0 through
A through F, which is base 16, I thought.
0 through 9, and A, B, C, D, E, and F. Yeah, I just used the letters here, okay? So, on this thing in the bridge, if A wanted to go to B, what would be its process? Ethernet, what's it going to do? Just go right there. What's the first thing it's going to do? Go listen to see if there's any other traffic. CSMA, carrier sense, multiple access, collision detection. Is there any traffic? No. Then I can send my traffic, and what's it going to have to do in order to get there? It's going to have to use the ARP protocol to find out what the MAC address is. We do all of that. So we go from A to B, no big problem, right? What if we wanted to go to E? A to bridge, A to hub to bridge to E, exactly. What the bridge does is keeps track of, similar to, much like the switch. We talked about the switch, we're going to talk about in a minute. Keeps track of the MAC addresses. Keeps track of the MAC addresses on each side of it. So this one also, since this traffic here, going from here to here, is also going to go to here, and going to go to here, and going to go to here, right? Because it's a bus. Everything sees it. This A to B, this is going to be the only one that accepts that traffic because they say, hey, this is my MAC address. What would happen here is the bridge would know that A, B, C, and D are up here, and E, F, A, and B are down here. So when it gets to this, it says, hey, A to B, it's okay. Stays up there. If A wants to go to E, just exactly like Ken said, he's going to go down here and says, and he's going to go to the bridge. The bridge says E is on the other side, so it's going to pass that traffic through to that segment. What we do is, what we've done here is isolate the segments so that if the traffic goes to something on its same segment, it doesn't go through the bridge. The other machines never see it. What it's really designed to do is to isolate traffic, minimize traffic. We're going to minimize collisions here by doing that. So that's what that thing, the bridge, is designed to do. Looks kind of like what we talked about a switch does, doesn't it? What does a switch do? Memorizes MAC addresses, except it memorizes MAC addresses by port. Sometimes a switch is called a multi-port bridge. The difference is this is done in software. Bridges bridge in software, and switches switch in hardware. Hardware is going to be the most desirable way to do things. So it connects two network segments, analyzes the incoming frame, makes decisions about where to send them based on the MAC address, just like my bad drawing did there. Operates at the data link layer. Protocol independent, because it doesn't matter here if it's TCP/IP, IPX, IPX, whatever. But in all honesty, protocol independent is not a real issue here because it's going to be IP. It's always going to look for filters on, makes decisions based on the MAC address. Move data more rapidly than traditional routers because it's at a lower layer. Anything that you can do at a lower layer is probably going to be faster. Extend the Ethernet network without extending the collision domain or segment, because we didn't increase the collision domain. And using the 543 rule, we could extend those and not create any more collision domains in here. Because how many collision domains do we have? Two, right? Because we had isolated it. Otherwise, if we just add another hub, we just extended the collision domain. Still one, it's just much bigger. Put more devices on it. More collisions. Can be filter out certain types of frames. Can be programmed to do that. then get back into mouse mode. Switches subdivide the network into smaller logical pieces. Can operate at layers 2, 3, or 4 of the OSI model. Can be called multi-port bridges. The layer 3 switch does a similar thing to a layer 2 switch, except instead of memorizing MAC addresses, it memorizes IP addresses, so that it knows where to send those things. Have internal processors, memory, and several ports. Sorry?
Does it do both, or just one of
It can do both. It can do either. So on a switch, you see, we gotta go through the switch again. So a switch has how many collision domains?
Virtually none.
Virtually none. How about virtually many?
Okay, virtually many.
Why do we want a lot of collision domains? Because everybody can have their own. But you're right. Eventually, what we're really talking about when we say they have a lot of collision domains is we don't have collision. So yeah, we don't have collision. So I understand why you say virtually any. So if we have these things and we have our machines hooked up to them, did I get too many again? Well, we'll start with one, because we can do one, right? 4, and we'll do these, A, B, C, and D. If one wants to go to anything else, use a different color for the traffic. Let's say that one wants to go to D. It's going to go in the switch internally, go to D. The first time through, what happens is we have this thing called the MAC table, and I said in Cisco they call it the CAM table, content addressable memory. That's what they call it. It's not MAC that the spell checker fixed for you. So we have port and MAC. So when this traffic goes into, we'll say, you've got a number of the ports, right? 4, 5, 6, 7, 8. When this traffic goes into port 1 has a MAC address of 1. It's recorded there. But it doesn't know anything else about any of these other ports, does it? Not yet. Not yet. So what's going to happen is, first time through, everything gets flooded, and that's the term that they use, out all the ports. So first time around, gets flooded out all the ports because it doesn't know where to send it, except for the port that it came in on. Knows it's not there because it came in on that port. When D answers, then we go over here and say that port 8, that didn't do so good, did it? Port 8 has MAC address of D. The next time that one or anybody wants to go to D, instead of flooding it out all the ports, it goes directly to that port. So that's why we don't have collisions. Full duplex, transmit and receive at the same time, which essentially doubles our speed.
Yeah, but because it's already flooding all the ports, and only one of them is answering, also isn't the other one's answering saying this is mine? No. It just, if you receive traffic at the layer 2 that's not to you, just drop it. That's what routers do too. If a router doesn't know what to do with something, just throws it away. Okay. So
No, they're not going to answer. Because the only one that answers is the one that the traffic's actually intended for.
So the next time, let's say if something comes from 1 to go to 4.
1 to go to 4, we're going to do the same thing. Let's use,
So it'll flood.
let's use this green guy. 1 to go to 4, right?
So it'll flood everything except for 1 and
That didn't work.
1 and
1 to 4, it won't go back to the port that it came in on, but it will flood, because it's a new one, it doesn't know where 4 is yet. And then when 4 answers, it says, hey, port 4 has MAC address 4. The next time something goes from 1 to 4, it goes directly there.
Would it flood D as well? Because it already knows who D is. It already knows that port 8 is.
But what if somebody changed the computer on D?
Well, I'm just saying.
Yeah, no, it'll still flood out D.
It'll still flood out D.
Yeah.
So the question is, now it's done this, it knows where 4 is, it knows where D is, it knows where 1 is. If D wanted to communicate to any of those 3, would it still flood, or would it know?
No, because B goes in here and says, hey, now I know if B wants to go to 1, right? B floods into, what is that, 6?
Yes.
It's going to say 6. It's got MAC address B. And it wants to go to MAC address 1. Well, I know where that is because it's right here. It's in the MAC table. The problem with that other one is, what if we put a different computer in here? These things are not permanent either. They have timeouts on them. The MAC tables, each of these entries has a lifetime.
So,
If they didn't, you could never change stuff.
but even if you changed it before they time out, doesn't it verify that
No. The problem with, if D was here, let's do another one. What if we put a hub down here that's got 6 machines on it? How many MAC addresses are going to be on that port? 6. That's one of the reasons it still has to flood it out. What if there's something else there? Well, the first time through, until it gets it into the MAC table, if it's going to that address, then it will only go to that address. See if I can actually make this thing work for me this time. Each port acts like a bridge, knows where the information is that it wants, receives its own dedicated channel once it is there. Installing a switch, it's a really tough one. What kind of cable do we use? RJ45 is a connector. Twisted pair, what kind of cable? Two. Actually, 3. We have a straight through, crossover, and a rollover. Rollover is specialized with Cisco typically. To the switch? Straight through.
Then I'd be jumping from one switch to another switch, then you use
Crossover.
But if you're going to a hub,
You use a? Crossover. Because they're both what are called channel connectors. When we get into routers, we'll have the DTEs and DCEs. Those are serial connectors, but this is channel cable. So they're both channel. The switch and the hub are both channel devices. We don't have one here, but crossover go from switch to switch, hub to hub, switch to hub, hub to switch are going to be crossover cables.
same with bridge.
Yeah, bridge be similar circumstance. Are you going to see a bridge? Odds are against it. You might, but odds are against it. Installing the switch, the reason that we want to do switches is by having that dedicated traffic, we've complicated anybody that's sniffing the network's problem, haven't we? Because what traffic do you see? Only the traffic between those 2 devices and the broadcast traffic. Broadcast traffic is stopped by routers, not switches. The different switch modes, and I think we talked about this a little bit. Switch running in the cut-through mode reads the frame's header and decides where to go forward. What it does is reads until it finds the destination address and sends it there. Cut-through cannot read the frame check sequence before it transmits, can detect runts The biggest advantage of speed of runts is a frame that's not big enough. We got giant runts and giants are two of the definitions of the frame sizes. Store and forward reads the entire data frame before it sends it on. It can do the frame check sequence, can check to see if the packet's been if the frame's been damaged. Slower than cut through because everything has to get there before it is resent. The other one is collision. We detect collisions. We read there's 64 bytes of data before we do those. Here is a different concept, and you're going to have an activity, so you may want to listen to this one. VLANs, virtual. We see we like a lot of virtual stuff, right? Virtual local area networks. What defined a local area network? I know it's small and in there, huh? We defined a lot of stuff at layer 2. A local area network, a network itself is going to be a particular set of IP addresses. What we can do with switches is configure them so that they separate the ports into different local area networks, and the only way for those things to connect together is through a router. So we can isolate those things. The advantages to that is if we, and what they're typically going to say, if we have, let's see if it does this, see if it goes on for me. If we have, maybe we got and this is going to be an ugly building, a building with 3 floors, and we have, well, let's say, comptrollers or somebody dealing with money on each of those 3 floors. Do we want their traffic to be visible to everybody? Or let's say you've got a building like this. Do we want financial aid traffic to be visible to everybody so that they can possibly get it? What we want to do is isolate it. So what we would do is take these switches and the ports and divide the ports into networks. And there's a couple of protocols have to be running. It's called the VLAN trunking protocol, VTP protocol, shares that information. So that if we had some of these people on the 3 floors, so we got a bigger switch up here, then we can set it up so that only the traffic that's on the virtual local area network, even though it's a single switch, there are different networks on it. What a lot of times we'll talk about is we have the red ports, and we have the red ports on each of these 3 switches. The red ports can only talk to the red ports. And then we got the green ports. Let's see if this will let me make green ports. The green ports can only talk to the other green ports. They can't talk to the red ports. And we have I think it'll let me make yellow ports. Big yellow ports. The yellow ports. If we want these devices to talk to each other, we've got to put a router out here. And what we would actually do is connect it in to one of these switches and have the protocols that allow all of the traffic. It's called a trunk port because all of the information goes on a trunk port. We connect these switches together using a process called trunking with trunk ports, which means that if I'm going from red to red, the traffic goes on the trunk port. When it gets to this switch, it says, oh, you go to the red. You go to the red ports. If we have traffic going from the green, it grows green up here, oh, your traffic only goes to the green ports. If we want to go between them, since they're different networks, we have to go through a router. So the router device will allow the networks to connect together, but you don't get all of the ability to do sniffing at layer 2 in order to do that. What this does is allows you to put employees that should be on the same network in different physical locations.
Now, when it floods, does it only flood?
Only, yeah,
Only the color that it's,
yeah, because they're,
unless it's on a router.
unless it's on a router. The routers route, and what we really would have here is called a router on a stick. We connect it into the switch someplace, and if we were going from red to green, it would go in the router and then come out and say, okay, now I want to go to the green port. Because they're on different networks, different IP address networks, different layer 3 networks. Yeah, this is, and most of the stuff that we buy, our small ones don't do this, although I've noticed that some of the newer ones actually do allow VLANs. When you go into wireless here, where can you get to? Nobody uses the wireless. You use the wireless, where can you get to? The internet?
You can get to the internet, but you
Can't get to any of the stuff in the building, right?
can't get to any stuff in the building. You also don't have free roam of the internet.
Yeah, that's a different filter, but
But
just to where we go. How do you think that happens? You get on the internet VLAN, and that's the only place it goes. It's not routed to anything else. Could we make it otherwise? Absolutely. Do they want to make it otherwise? No. So, VLANs segregate traffic. Switches, honestly, are probably the most versatile device that you have. As I've already talked about in here, we can do port security. If you unplug one of these computers and plug your laptop in, it's going to shut the port down. So we can control security at layer 2. We can divide our network up so that we can physically change the location of individuals and they're still on the same network. In my opinion, what should they do in here? This instructor machine out here ought to be on should be on the instructor subnet. We could do that with VLANs. You guys should all be on this room VLAN. Room 108 should be on the 108 VLAN, so that we can go back and configure the ports to be members of specific virtual local area networks, and you separate the traffic. It's a really handy tool to have, and they really are very versatile when you look at them. Very versatile devices.
so why would you want a hub?
You wouldn't. The reason that we still have... Okay, why would you really want a hub?
Yeah.
Let's say that I wanted to I wanted to monitor all of the traffic going out of my building. How would I be able to do that? Now, honestly, there are two ways to do it, because switches have this thing called a span port, sometimes called a mirror port, which says that I can watch all the traffic on one port from another port. So I could do it that way. Or if I really wanted to make a mess, I could just flood the hub, flood the MAC table, and if the MAC table gets full, and that goes back to how big a switch do you want? If the MAC table gets full, it becomes a hub. So if I was hacking, what would I want to do? I want to make your switch a hub, don't I?
Yeah.
How can I do that? I can flood it. If I can't get onto it, I can create a span port so that I can watch all the traffic on my port, or particular traffic on my port. So it monitors, it mirrors one port to the other. But if they're running correctly, they're really the device that you would want. Logically separate networks within networks, kind of what we talked about. We have different layer 3 networks, multiple layer 3 networks on a single device. Switches to group the number of ports into a broadcast domain. Combination of ports making up a layer 2 segment, the TCP/IP are referred to as a subnet. And we'll get into subnetting and all sorts of fun in the next block. Created by properly configuring the switches software, and it's really not a very difficult task to do it. Layer 3 switches are basically routers that route in hardware, for lack of a better description. They're kind of interesting is because they're switches first, and the way that you make a layer 3 switch port a routable port is you tell it's not a switch port. And then you can put an IP address on it and make it a routing port. The ability to interpret higher layer data enables the switches to perform advanced filtering, statistic keeping, security functions. What it does is it allows it to do the layer 3 stuff. Different filtering at layer 3, layer 4 than we can do at layer 2. A lot more than we can do at those layers. Routers are layer 3 devices, IP devices. Can integrate LANs and WANs running at different transmission speeds. Routers can actually be protocol translators. You have one of those at home probably, don't you? Because your wireless device is a protocol translator. It translates the 802.11 to 802.3. Routers can do the same thing. We can have LAN and WAN ports going into it, and it can take it from a local area network protocol, Ethernet, and translate it to a wide area network protocol so that it allows networks to come together. And it finds networks. Reads the logical addressing information, layer 3, IP addressing information. Operates at the network layer, protocol independent because we can have multiple protocols running on it. And again, the only protocol we're really going to have running on is going to be IP. Internal processor, operating system memory, and all of those other things. We got one, I thought, with the top off of it back here. But they're really pretty unimpressive looking devices. I guess they took it. All they are little flat devices. On the back of them, we've got the ports that we can use. We can have serial ports or Ethernet ports that are available on them. This one's got serial, it's got a console and an aux port. Console allows you to connect to it in order to manage it. And this is where the serial port on the computer comes in handy, because it's got a serial port to what's called a dongle. Dongle connects to the serial port, translates the serial port to an RJ45 using a rollover cable. Rollover cable, when you make them, one with the tab up, one with the tab down. Simply. 1, 2, 3, 4, 5, 6, 7, 8, 8, 7, 6, 5, 4, 3, 2, 1. So if you make one tab up, one tab down, you've got a rollover cable. Modular router, multiple slots, whole different interface cards. This one is not a modular router. If you look at the other ones back here, these newer ones, turn this around here hopefully without turning it over. On the back, we've got just plates on here that we can take off, and this one you can see has got screws on it. You can take the module out, so you can actually put different capabilities into these things. So that's what the modular means, that we can put different ports into that. And when we look at the packet tracer here in a few minutes, you can do that demonstrate on packet tracer virtually how you would do that. All routers can connect dissimilar networks, interpret layer 3 addressing information, the best path for data flow, reroute traffic. Can determine best path. You can determine best path because we're going to have two different types of routing protocols, dynamic and static. Static is when we tell it how to get from point to point. Dynamic is when we configure a protocol to allow that to happen. Stops broadcasts, prevents certain type of traffic from entering the network. We can filter what goes on the router. We usually call it a filter router. You can actually configure one of these things if you've got a smaller network as a firewall, to where you filter out what you want to do. Interior router directs traffic data between nodes and autonomous LAN. Sorry?
How's that different from like a proxy server?
A proxy server runs at layer 7, actually. It runs at the application layer. A proxy server,
Layer 7 device.
yeah. A proxy server takes your request, which you do here. You say you want to go to www.something.com. That request goes to the proxy server. The proxy server then rebuilds that request and sends it from its IP address.
To check it to say, okay, this is all.
It can, depending on what you do. We do a little bit of that. We don't do a whole lot of that anymore. Most of the messages that you get are from the firewall, which also, yeah. The red screen, blue screens are from here, and that's just from stuff that's left over that nobody's ever taken out.
Something on here and it says you can't go to this page.
Yeah, yeah. So there are a number of filters that go from here. The answer is maybe. If you get a red screen, blue screen, because there's filters on both of them.
I get the red string often.
The red screen, and that's just because of a character string in there somewhere, because we have these places that you go are like 100 miles long. The problem with filters with a proxy server, if we wanted to filter out, and I probably said this earlier on, but we'll say it again, if you wanted to filter out the character string SEX, you could do that.
Oh, yeah.
The problem is when you wanted to go to Essex County, England, that character string's in there. So it's going to give you the same filter effect.
And there's no way to say specifically, just...
There are a number of ways to filter, yes. You can do it by character string, you can do it by IP address, and on and on and on and on and on. There are a number of old filters that are still left on this proxy. They really had a huge problem when they started the medical program,
Yeah.
because about all of their terms get filtered.
Me and Neuron were talking about that.
Yeah. Interior router, what you're typically going to have, another bad drawing, in a networking environment is we have our famous cloud that's going to come into, the internet's going to come into a filter router, to a DMZ, to a firewall, and then it's going to go to the internal router, which you saw in the NOC the other day, which is a layer 3 switch, which is the router. And from it, you're going to then route to however many networks you have inside your local area network. In our case, there are multiples here. We have multiple networks that are available inside the building, an internal router to do that. You don't have to have a layer 3 switch. You can use something like a Linux router if you wanted to do things like that. Exterior router directs data between nodes external to the given autonomous LAN. Honest to goodness, what happens is you send it to the ISP and then they got to figure out what to do with it after that. We don't really do a whole lot of that. Border routers connect autonomous LAN with a WAN, the filter router that we showed going to the cloud, to the internet. That would actually be going to the ISP. Static and dynamic routing. We'll look at this in more detail in the next class. To take away today, static routing, network administrator tells the router where to send the packet. A router is very much like your the directions that you get in your car. How much information do you have when you're driving down the street? What does your device tell you?
And do not do meters. Turn right.
Turn right. It just knows what the next turn is, right? Inside there, you can get a turn list. True?
Yeah.
And it knows everything that you're supposed to do, and that's what dynamic routing would have. That would be the internal part. It would know a lot more. All a static route knows is how to get to the next network. How to get to the next network. How to get to the next router. So we put that information in there, and again, we'll look at that, but after we've talked about IP some. So hopefully it'll make a little bit of sense. Dynamic routing protocols, static routing protocols, we do it. Dynamic, we set the computers up, or the routers up so that they share information and are able to create their own route tables. Router A, okay, if we were doing statics here, switch A, we would have a default gateway. The default gateway is simply the router that we go to get someplace. So the default gateway would send it here. If we were going to work group B, and we'll say that's a network, work group B, we'd have a route in here that says, hey, to get to work group B, go to this IP address. And then routers know about networks that are directly connected to them, so that's when we have to stop giving it directions. What you do is tell it how to get from router to router to router. RIP, OSPF, EIGRP, BGP. Lots of great letters here. RIP, OSPF, and EIGRP are called interior gateway routing protocols that are in local area networks. BGP, border gateway protocol, is what the internet runs on. It's outside of it's a large area routing protocol. These are, and again, what we need to know right now, basically what these are. You'll have the opportunity to configure these multiple times in the Cisco classes and some in the Windows classes. Configure them as routers. What they do is find the most efficient path between nodes, kind of, depending on how they determine that. Communicate via routing protocols. Routing protocols are the protocols that routers use to talk to each other. And those routing protocols are the RIP, OSPF, and the EIGRP. We won't really worry about BGP except to know that it exists. So, open shortest path first, interior, enhanced interior gateway routing protocol, and routing internet protocol are what the letters stand for as we do these things. B routers or bridge routers. This is another device that kind of like to know what it is. You're not going to see one. It's a bridge and a router. I guess we could kind of think of that as the first version of a layer 3 switch. Gateways connect two systems using different formatting communications, going from a desktop machine to a mainframe to do work on the mainframe. Email gateway, internet, LAN, security, a number of different gateways that are available on them. And again, gateway is one of those terms that can mean different things depending on how it's used. And you thought I was never going to get here, didn't you? The protocols are something that we will do. You're going to get sick of them when we go in there. The routing stuff to take away right now is there's statics, which we put the information in, and dynamics, which allow the routers to share the information. Statics tend to be more secure, although if you properly configure dynamics, not such a big deal. Adapters, we talked about those, desktops, towers, and all that other. NICs, they spent about half the chapter on NICs, something that we're probably not going to have to configure because they come that way. Hub is a layer what device?
Layer 1.
Layer 1. What does it do?
It
makes a mess.
Repeater.
Repeater?
Also connects devices.
Connects devices together, so it becomes a multi-port repeater, right? And a repeater regenerates the signal, not amplifies. Bridges, what do they do? Same thing, but at layer?
4.
Really?
No, 3.
Really?
Okay,
2.
Finally.
Yeah.
Can I phone a friend or what?
Yeah. What?
Phone a friend?
What's good about a switch?
Do a street shot.
No collisions.
No collisions. Why?
Collisions,
No collisions.
well, no collisions.
No collisions. Why? Lots of collision domains.
Yeah, like a lot of collision domains.
Every connection gets its own collision domain.
The more collision domains, the less chance of a...
More collision domains? It's just like getting your own private highway. Your own private divided highway. The more of those there are, the less chance you're going to have a collision with somebody else, huh? Same thing there. How does it do that? Records the port number and the MAC address so that after the first connection, it knows where directly to send the traffic based on the MAC address. Bridge or hub, the bridge establishes a filtering database. The bridge, a switch, sometimes called a multi-port bridge, because the bridge had a list of MAC addresses on each side of it, so they only passed through the traffic that needed to go through in order to go there. Subdivide the network to smaller logical ones. A router multi-port device can connect dissimilar networks, LANs, WANs, and what do routers find? Other networks. What finds the individual machine once you find the network? What address? MAC address, using the ARP protocol, Address Resolution Protocol. We looked at one of those. It says, who has whatever the IP address, and then the answer is whatever MAC address is has that, and it is it's a broadcast and then a unicast when we go through those things. Router is protocol dependent. You can have multiple protocols running on a router if you needed them. We don't really need them anymore. As a matter of fact, I think that Cisco's actually taken IPX out as a protocol that's available on their routers. TCP/IP. Questions? I know you're just ready to scream now, right? Let me take a break and let me set up Packet Tracer and